how the stars, those tiny specks of light in the night sky, came into existence? Our story begins in the boundless cosmic theater, where nebulae, the colossal clouds of dust and gas, play a vital role. These aren't just ordinary clouds, but the cradles of starbirth. The nebulae, teeming with hydrogen and helium, are the raw materials that the universe uses to craft its shining stars. Imagine a nebula, a vast expanse stretching over light years, silently floating in the cosmic ocean. Within this nebula, an interesting phenomenon takes place. The particles of dust and gas start to feel an invisible pull, a cosmic tug of war orchestrated by the forces of gravity. Slowly but surely, these particles begin to clump together, drawn towards a common center. As more and more matter congregates, the center grows denser and hotter, forming what we call a protostar. This embryonic star is just the first step in a long journey. But don't be fooled by its humble beginnings. This tiny entity is destined for a fiery and brilliant future. The protostar continues to amass more matter from its surrounding nebula, growing bigger and hotter. Its core blazes with mounting intensity, and the pressure within mounts. Eventually, the conditions within the protostar's core reach a critical point. At temperatures of several million degrees, hydrogen atoms in the core start to collide with such force that they fuse together, creating helium. This process, known as nuclear fusion, releases an immense amount of energy, causing the protostar to shine brightly. This ignition, this first spark of light, marks the birth of a new star. Now the star is ready to embark on its stellar journey, illuminating the cosmos with its radiant light, playing its part in the grand cosmic ballet. Welcome to GSD Brainers, the place where curiosity meets discovery. Now that our star is born, what happens next in its stellar journey? Let's delve into the fascinating life of a star. The majority of a star's life is spent in a phase called the main sequence. This is the star's prime time, its heyday, if you will, where it's burning hydrogen into helium. This process, known as nuclear fusion, is what gives the star its brilliance, its energy, and its heat. It's like the star's engine, constantly running, constantly fueling its existence. Now imagine a cosmic tug of war taking place at the heart of each star. On one side, we've got gravity, ceaselessly pulling everything inward. This relentless force is forever trying to crush the star under its own weight. On the other side, we've got pressure generated by the nuclear fusion pushing outward. This outward push is what keeps the star from collapsing under its own gravity. This ongoing battle between gravity and pressure is what keeps the star stable. It's a delicate balance, a cosmic dance, if you will, where neither side gains the upper hand for most of the star's life. Now, you might be wondering, why do stars come in different sizes, colors, and lifespans? Well, the answer lies in their mass. The mass of a star determines its destiny. Larger stars burn hotter and brighter but live fast and die young. They go through their hydrogen fuel at a rapid pace and have shorter lifespans. On the other hand, smaller stars, like our own sun, burn their fuel more slowly, leading to a longer existence. They may not be as flashy as their bigger counterparts, but they sure do last. The color of a star is also determined by its temperature, which is a direct result of its mass. Hotter stars appear blue, while cooler stars are redder. In between, we've got a spectrum of white and yellow stars, including our sun. This delicate balance between opposing forces defines the life of our star. Every star, no matter how bright or massive, must eventually meet its end. But how does this happen, you may ask? Well, let's delve into this fascinating cosmic tale. Stars, those magnificent celestial bodies that twinkle in our night sky, are nothing more than giant nuclear reactors. They spend the majority of their lives fusing hydrogen to produce helium in a process known as nuclear fusion. This process releases an incredible amount of energy, causing stars to shine brightly. However, this fuel isn't infinite. Eventually, stars exhaust their hydrogen reserves, and this is where their fate diverges based on their size. Let's consider smaller stars first, like our very own sun. When these stars exhaust their hydrogen, they start fusing helium to produce heavier elements like carbon and oxygen. This causes them to expand dramatically, transforming into what we call red giants. Over time, these red giants shed their outer layers, creating a beautiful glowing shell of gas known as a planetary nebula. What's left is a dense, hot core termed a white dwarf. These white dwarfs will continue to cool and fade over billions of years, eventually becoming black dwarfs, the final stage of a star's life. On the other hand, we have the larger stars, those that are several times more massive than our Sun. These behemoths also transform into red giants when they exhaust their hydrogen, but their story takes a more dramatic turn. Their immense gravity causes them to fuse heavier and heavier elements until they reach iron. Fusion of iron doesn't produce energy, it instead consumes it. This disrupts the delicate balance between gravity pulling inward and the outward pressure from fusion. The star's core collapses under its own gravity, triggering a colossal explosion known as a supernova. What's left could be a dense, spinning neutron star, or if the star was massive enough, a black hole. In death, as in life, stars continue to astound us with their spectacular transformations. This cycle of birth, life, and death of stars is a testament to the dynamic, ever-changing nature of our universe. Did you know that the death of stars isn't the end of their story, but a new beginning? The celestial bodies we admire in our night sky are not mere objects of fascination, but they are also cosmic architects, creating and recreating the universe in a continuous cycle of birth, death, and rebirth. When stars die, they do not go quietly into the night. Instead, they explode in a brilliant supernova, scattering their remnants across the cosmos. These remnants, rich in heavier elements such as carbon, nitrogen, and oxygen, linger in the universe, forming nebulous clouds of gas and dust. It's within these cosmic dust clouds that the foundations for new stars are laid. Over countless millennia, the gas and dust in these clouds are drawn together by the force of gravity, condensing and heating up until a new star is born, igniting its nuclear furnace and beginning its journey through stellar life. But these stellar remnants contribute to more than just the birth of new stars. The heavier elements they contain are also the building blocks for planets. As new stars form, the material that doesn't get sucked into the star forms a disk around it. Over time, particles within this disk begin to stick together, gradually growing larger and larger until they form planets. And it doesn't stop there. These elements are essential for life as we know it. Carbon, nitrogen, and oxygen, along with other elements forged in the heart of stars, are the ingredients of DNA, the blueprint of life. So in a way, we're all made of star stuff. Our universe is a cosmic dance of creation and destruction where the death of a star marks the birth of new stars, new planets, and potentially new life. We owe our existence to the stars that came before us and the elements they left behind. Stars, in their death, sow the seeds of new life, shaping the universe as we know it. Through their legacy, we are all children of the stars. What does the far future hold for the stars in our universe? As we gaze into the cosmos, we find ourselves drawn to the question of what lies ahead for the universe and its glittering inhabitants, the stars. The fate of the stars and the universe is tightly intertwined and primarily depends on two crucial factors: the rate of the universe's expansion and the enigmatic nature of dark energy. One theory that paints a picture of the universe's far future is the heat death scenario. This postulates that as the universe continues to expand, stars will eventually run out of fuel. The cosmos will become a vast, cold expanse with only the faintest embers of white dwarf stars to pierce the darkness. As these too cool and fade, the universe will reach a state of maximum entropy or heat death, where all energy is evenly distributed and no work can be done. In contrast, the Big Freeze theory suggests that the universe's expansion will continue to accelerate, driven by dark energy. In this scenario, galaxies will drift apart until they are beyond the reach of one another. The stars within these galaxies will burn out, and the universe will freeze in a state of extreme isolation and cold. Yet another possibility is the Big Rip. Here, dark energy's strength increases over time, causing the universe to expand at an ever-accelerating rate. Eventually, this force would become so strong that it would tear apart galaxies, stars, planets, and even atoms themselves, leading to a universe that is essentially torn to shreds. While these scenarios might seem gloomy, they're a testament to the awe-inspiring dynamism of the universe. The star's unending cycle of birth, life, and death has been the engine driving the universe's evolution, leading to the creation of planets and life as we know it. While the future of the universe may seem bleak, remember that it is the star's unending cycle of birth, life, and death that has brought us here, pondering these extraordinary celestial wonders. Until next time, folks, stay curious For more brain-boosting content, hit that like and subscribe button. Thanks for watching.